Do you have any homework questions you'd like to ask? Yes.
Number 12 says, on the first limit, x goes to 0. Tangent of 7x over sine of 4x.
Okay, so what we have to know in order to do this problem is that if we replace x with 0, both the tangent and the sine of 0 is 0. Okay, tangent of 0 is 0, sine of 0 is 0, so we have the form of 0 divided by 0. So let's see, I'm gonna write that down right here. Here. We're going to try eventually to use our special limits. And the limit as x goes to 0 of the sine of any number times x divided by any other number times x. We eventually just give you the ratio of the numbers in front of the x. The other special limit comes from this one, is that the limit as x goes to 0 of 1 minus the cosine of x divided by x. Does anybody remember? This one? This one's 0. This one is 0. That one without the k and the m is 1. With the k and the m is whatever the k and the m are. So our problem in this example is the tangent. We need to get that out of there. So let's write the tangent of 7x as the sine of 7x divided by the cosine of 7x. And then all of that's divided by the sine of 4x. And let's put all that in the same line. Dividing by that sine of 4x is the same as multiplying by 1 over the sine of 4x. Now the cosine's not giving me any trouble, so I'm going to take that factor of 1 over the cosine 7x, put it way out here on the end. Just isolate the signs for now. So I'm going to write that as the sine of 7x divided by 1 times 1 over the sine of 4x, now times 1 over the cosine of 7x. And the general form of this special limit says, or the less general form, the specific form says that the sine of x over x is going to be 1. So I'm going to make that show up where I just have the sine functions. I'm going to put the version of the angle in the denominator. There they are. So I need a red one. So I'm going to put a 7x right here, and I can do that if I put it down here. So it dots in the wrong spot. And I take it out up here so that I'm multiplying by 1. I'll do the same thing here. I'm going to put a 4x here. But I'm going to take it out right there. Now I'm going to take this one and that one and put them together in front. So here's that 7x, here's that 4x. Then I have this. Then I have this one. And then I have that one. Everybody following this? So I can cancel here. So I just have 7/4 from that. I can take my limit term by term. This limit then follows that same pattern as either the top one I wrote or the bottom. When this part matches that part, then x goes to 0, the sign of blah over the same blah goes to 1. This is just the upside down version of it. So I can think of that as 1 over the sine of 4x over 4x. So the 1 stays put on top, the bottom goes to 1. So this one also goes to 1. Now I'm going to let x go to 0 here, and I get the cosine of 0. Quick, what's cosine of 0? That's also 1. So this last term goes to 1. So here's our final answer. 7/4 times 1 times 1 times 1. Okay. What else you got for me?
I couldn't get the answers for number 2. It's f of s is equal to the absolute value of 3 minus s over 3 minus s, and then s is not equal to 3.
Okay.
And it had like a, b, c, d, and it's just the limit as s goes to 3 from the right, and then b is the limit as s goes to 3 from the left,
Okay.
and then c and d are the same thing.
All righty. So at S, does everybody agree that this behaves like 0 divided by 0? So what we have to do is look at what happens near S. And then in the first two, you said from the right comes first?
Yeah.
S goes to 3 from the right. So usually when we get 0 over 0, like we did in this last example, you do some manipulation. But there's nothing that we can do here other than just plug and chug. Pick numbers near 3, but slightly bigger than 3, plug them in and see what happens. Pick numbers near 3, slightly smaller than 3, plug them in and see what happens. If you have any idea of what the absolute value of x over x looks as its graph, then that helps somewhat too. But if you don't, we'll just do this. I'm going to make a column for S and a column for 3 minus S in absolute value divided by 3 minus S. So first pick numbers slightly bigger than 3. Maybe that'll be enough to see what the pattern will be. And I think you can do these without a calculator, right? 3.1 minus, 3 minus 3.1 will be a negative 0.1 in the absolute value bars. On the bottom, I have that same difference, but without the absolute value bars. So I'm going to get a positive 0.1 over a negative 0.1, which is a negative 1. I put this one in, 3 minus 3.01 is going to be a negative 0.01. But on the bottom, I have a positive, a negative 0.01. Positive comes from the top after we take the absolute value, and the negative comes from the bottom, but it's the same number. So again, we get negative 1. Am I going out on a limb to say that this one's going to be negative 1 as well? Can you see that no matter how close I pick this to 3, the numerator and denominator have the same value, but opposite in sign. So that makes this limit negative 1. Let's go the other way. Pick numbers slightly smaller than 3, but make them get closer to 3, like 2.9, 2.99, and maybe again, 2 values will be enough. So put that in on top. 3 minus 2.9 is 0.1. I've got the absolute value of 0.1 divided by 0.1. This time they're both positive. Positive 0.1 over positive 0.1 gives me 1. Same deal happens here. 3 minus 2.99 is 0.01, and that's 0.01. So there it's going to go to 1 as well. So if this were asked, the limit without regard to direction near 3, what would you say? Doesn't exist, because there's a jump in the graph right there. There's my does not exist. That's the only problem spot. All the other points are values of S at which this has, whoa, what happened there? A little tomato soup on me. Golly, that's pretty. If I put in a 0 for S, I'm good. I don't get 0 over 0. If I put 5 in for S, I'm good. Any other number other than 3 has a value on this function. And we said if you could put the number in and get a number back out, then that's your limit. So for the other two parts, that's all you do, is plug whatever the number is, even if it is a one-sided limit or not. Okay? What else? Yes, sir.
Number 14, it's a limit as x goes to 7. And then in parentheses, 1 over x minus 1/7 all over x minus 7.
So what happens at x is equal to 7? Zero over 0, right? Try to plug 7 in. We get 1/7 minus 1/7 over 7 minus 7. So we got to do more. And it's kind of telling us what to do. Subtract two fractions. But to subtract fractions, you've got to get a common denominator. So I'm going to multiply this by 7 over 7, this by x over x. 7 over 7. X over x. So now they both have a denominator of 7x. The first fraction has a 7 here. The second one has an x there. Now I'm going to flip and multiply. Treat that as x minus 7 over 1. Flip it over. And have you seen enough of these to know that this is just minus 1 times that? So I can cancel and leave a factor of minus 1 on top. And so now I'm left to take the limit as x goes to 7. On top, I'm going to have minus 1, on the bottom 7x. So this, putting it together and flipping and multiplying, got rid of the 0 over 0 factor. Now I can just put 7 in for x. And I get negative 1 over 7 times 7. It's 49. Okay. Another? Okay. Then what I'm going to do today is talk about continuity. And then I realized, well, maybe it's not as obvious to you which functions are continuous and which aren't. And make sure you know not all of our functions. So let me get more to the board. This is going to drive me nuts that I got such a little bit to write on. Let's do it. Much at all. So in section chapter 2, I'm thinking it's 2.3. So roughly what we said was that if you've got the formula for a function and you try to sketch its graph, and you're able to sketch its graph without picking up your pencil, then you've drawn the graph of a continuous function. Function is continuous at a point if, well, at a particular point, three things happen. If the first thing is that the value of the function actually exists at that point, you plug a number in, you get a number back out. The next thing you need is the limit as x goes to a of that function to exist. And the third thing you need is that both of these numbers are the same. That f of a is the value of the limit. So I'm going to draw you three graphs in which the function is not continuous at a point, and you'll tell me which of these three cases doesn't hold. So here's examples of function f is not continuous at x is a. First one, x is a, and I'm going to make it a vertical asymptote. The second one, here's x is a, and I'm going to put f of a right here. I'm going to make a jump in the graph. That x is a. And then the third one, I'm just going to draw a graph where that x is equal to a. I'm going to take a point out and move the point, say, to here. So in each of these examples, one of those three conditions, so I'm going to put the word and here, all three things have to hold. At least one of those three things is violated by these pictures. For the top picture, which of the three are violated? The first one and the second one, right? There's not a limit and there's not a function value. So here f of a does not exist. And the limit as x goes to a does not exist. That makes it not continuous there. There's a big rip in the graph. You can recognize that by typically it's a function that has a denominator. And it's a place where the denominator is going to be 0, but the numerator is not 0. The value of x that makes the bottom 0, but doesn't make the top 0. All right, which of the three parts is violated in the middle picture? The second one, there is no limit, right? I've got to value a function, but I don't have a limit because the two one-sided limits aren't equal. So here, the limit as x goes to a of f of x does not exist. Typically, you see that in piecewise defined functions. If you're given a function that says it looks like this if x is in this interval, it looks like this if x is in that interval. But we saw another example of this looking at the absolute value function. The absolute value of an expression divided by itself usually has a jump like that in it. All right, which of the conditions are violated in the last picture? Which one?
Number 2.
I've got a limit.
Oh.
There's just a hole missing. I get a limit right there. The third one, the limit and the function value are two different things. So this one, the limit as x goes to a of f of x is not equal to f of a. A hole occurs typically if you have a function and you take the limit and you get 0 over 0. But you're able to do some sort of algebra to eventually get a limit. That means we've got some sort of hole right there. Okay. And whether or not there's a point doesn't matter. So this type of discontinuity is called a jump discontinuity. This type of discontinuity is called a removable discontinuity. To remove it, we just redefine the function at that point. So when we pick this point up and put it in that hole. And this one is just called, let's just call it a rip, or a vertical asymptote. So if it'll have a discontinuity if it has something like one of those three things. If a function is continuous at every value of x, then we say that it's continuous on its domain. So we got to kind of know some graphs. Some examples. Of functions that are continuous for all values of x. Well, all polynomials, right? You pretty much draw those lines, parabolas, third-degree functions, and so on. Sines and cosines. Rational functions where the denominator is never 0. So I'm going to say for all x in their domains. Because I want to put square root functions here. Cube root functions. What other functions do you know how to draw? I need to have some idea. Back in chapter 1, I probably should have gone over this. A list of functions that we should all know. So let's do that now. Let's make a list of functions that we should all know how to graph. So let's back up a step. Do you know the graphs of, so my first one is going to be y is equal to x. Y is equal to x squared. Y is equal to the square root of x. Y is equal to x cubed. Y is equal to the cube root of x. Y is equal to 1 over x. And y is equal to the absolute value of x. Did we go over those graphs? If I gave you $1 for each one that you could just whip out like that, is anybody walking away with $7? I'm not gonna give it to you, I don't have $7. Test yourself if you know any of these graphs, see if you can draw them. I'll try to get the tomatoes to go. Stay. That's right. All right, let's check. Let's check what you did. Y is equal to x has the ordered pair 0, 0, 1, 1, -1, -1. And y is always x. Let's just align, diagonal line through the origin. Not so wiggly as I've drawn that one there. Y is equal to x squared. Got your parabola opening upward. So far, so good. Y is equal to the square root of x is only defined when x is 0 or more. We can't take the square root of negative numbers. So if x is 0, the square root of 0 is 0. If x is 1, the square root of 1 is 1. Now if I go out here and x is 4, the square root of 4 is 2, and so on. So it's a continuous curve that grows real slowly. Kind of like the top half of a sideways parabola. Y is equal to x cubed, passes through 0, 0, 1, 1, 2, 8. So 2, 8, let's go way up here. And then -1 cubed is a -1, and -2 cubed would be a -8. So it's got some symmetry through the origin, and then it turns up over here. Concave down to the left of the origin, concave up to the right. We can take the cube root of positive numbers or negative numbers. So this one's defined everywhere. It's just even roots that are defined for positive x. So if I start plotting some points, cube root of 0 is 0. Cube root of 1 is 1. Let's see, the next number I can take the cube root of in my head is 8. The cube root of 8 is 2. So if that's 1, 8 is way out here before it hits 2. Do you know what the cube root of -1 is?
Negative.
It is. So this is going to be another graph that has symmetry through the origin. It's going to look like that. Now 1 over x has a place where the denominator is 0. And that's right there at x is 0. So the y-axis, what's my ink here? The y-axis serves as the vertical asymptote. And if x is a fraction that's positive, 1 over a fraction is big. But as x gets bigger, 1 over x gets smaller. But it won't be negative unless x is negative. If x is negative, it does the same thing over here. In our examples, y is equal to x, y is equal to x cubed, y is the cube root of x, and y is 1 over x are called odd functions. Odd functions are symmetric to the origin, as if I were going to rotate this 180 degrees, I'm back on the graph. If I rotate that 180 degrees, I'm back on the graph. They're odd functions, and the powers on them are odd. Odd functions are symmetric to the origin. Y is equal to x squared, y is equal to x to the 4th. Those are called even functions. The cosine was an even function. What it does on the positive side of the x-axis, it does the same thing on the other side. Even functions have symmetry about the y-axis. Odd functions have symmetry about the origin. This is a function that's neither even nor odd. It has no symmetry about the axis because there's no graph over there. The absolute value of x, take this graph, take the absolute value of all the x's, and all the y's become positive. The y's that are positive stay there. The y's that are negative flip up here. And so you get this V-shaped graph. Then we went over the graphs of the sine, cosine, tangent, and then the inverse sine, inverse cosine, inverse tangent. I want you to know those graphs because functions are continuous for all values of x in their domains. So you got to be able to picture what x's I'm allowed to graph. Now, if I take a graph and do something like this, suppose I want to graph y is equal to x minus 2 squared. That graph looks just like that one, but what does this do in terms of a shift? Shifts it to the right 2 units. What about this one? That makes a shift. Which direction? Up. I'm adding something to the y. Here I'm subtracting from x. The x moves in the opposite direction that you think, but the y values follow the y's. Okay. So if you know those, you know all of them. For instance, I guess let's add one more. Let's add the number 8 here to be the absolute value of x over x, because that's something that appears many times in our limits. This one has a discontinuity at x is 0. If x is bigger than 0, the absolute value of a positive number is that positive number. So I'll always get 1. If x is a negative number, I'll get -1. And so if I do some sort of shift in there, it just moves it over to that value. For instance, if we look at the absolute value of x minus 2 over x minus 2. That's the same graph, but now the discontinuity is not at x is 0, it's at x is 2. Still looks like pieces that look like 1 and -1, but moved over to x is 2. When you switch the order of those, well, then it flips the graph the other way. Like in the example that we had 2 minus s. It flipped it that way instead of that way. But it'll always be some sort of jump in it. All you gotta do is plot a few points and you can figure out which one it is, this one or that one. It'll be one or the other. Okay? We need that so that we can recognize which functions are continuous. If I write out some functions, I want you to be able to tell me where it's not continuous by telling me the numbers that are not in its domain. For instance, for which x are following continuous. My first one, f of x is equal to 4 over x plus, let's make it 2x plus 1. This function belongs in this family. Its graph is going to look like that, but I've done some shifting to it. The 4 and the 2 stretch the y values. The adding 1 is going to do something that moves the graph left or right. So when you're answering this question, you're going to say, well, it's continuous for all values of x except for the one that makes me divide by 0. Which value of x gives me 0 in the denominator? Set that equal to 0 and solve for x and tell me what you find. Negative 1/2. So for all x not negative 1/2. Okay, so it's continuous for x other than negative 1/2. All right, what about this one? X plus 2 on the top, x squared minus 3x minus 10 on the bottom. So I'm essentially asking you the same question. Can you find the values of x that make the bottom 0? Can, then you know where it's not continuous, it's continuous everywhere else. You can't have the denominator equal to 0. Can you factor that now? Are there factors of 10, opposite in sign, that add to negative 3? 2 and negative 5. So x plus 2, x minus 5. Now set each of those factors equal to 0, and I get x is negative 2, and I get x is 5. So to answer this question, I'm going to say it's continuous for x not negative 2, and for x not 5. But these are two different types of discontinuities. If I have a factor of x plus 2 on the bottom and a factor of x plus 2 on the top, I'm able to cancel it and take a limit. So the value of f doesn't exist, but the limit exists. Which of the pictures that I drew up there of the discontinuities has the characteristic that the value of the function exists, but the limit doesn't? The other way. The limit exists, but the value of the function doesn't. That's removable. There's a hole in the graph when x is negative 2. There's a hole right here. There's a common factor. The value of x that makes that common factor 0 shows up geometrically as a hole. X is equal to 5 makes the bottom 0, but not the top. So what feature in the graph is that? Well, the bottom is 0, but the top is not. It's undefined, so what does that look like on the graph? There's not a value of the function there. There's not a limit there.
Right.
That's a vertical asymptote. So if you think about canceling the factor of x plus 2, then this function behaves like the graph of, if I cancel that factor, that leaves me the other factor, 1 over x minus 5. So its graph is going to have an asymptote at x is equal to 5. Right? It's going to look, I just erased it. One side up, one side down, but at x is 2, there's a hole in it. So here's x is 2. I put a 2 there, 2 minus 5 is -3, so there's a hole at 2, -1/3. If x is 0, I get -1/5, which is down here, so it's going to look something like that. And then up here, it's going to be something like that. It's a hole in it and a vertical asymptote. So I had to pick up my pencil twice to draw that graph. All right, so let me list you some properties of continuous functions. So in my discussion here, we're going to suppose I have two functions, f and g. Suppose f and g are continuous at some particular x value, say x is equal to c. Then each of the following are also continuous at x is equal to c. Any number times the continuous function would be continuous at x is equal to c. So take the graph of y is equal to x, it's continuous for any x. So is the graph of y is equal to 5x. That's just a line that has a steeper slope. Y is equal to sine x is continuous everywhere. 2 times sine of x is continuous everywhere, just changes the amplitude. Adding continuous functions together makes a continuous function. So does subtracting them and multiplying them. For example, y is equal to x is continuous for all x. Y is equal to the sine of x is continuous for all x. So x plus the sine of x as a function is continuous for all x. Y is equal to x minus the square root of x is continuous for all x for which they are both defined. Square root of x is only defined for positive x, so I would say that this is continuous for all positive x. Give me a 0 there. Continuous on their domains. F times g. If I take y is equal to x squared times the sine of x, that's going to be continuous everywhere because x squared is continuous everywhere. Sine of x is continuous everywhere. Now that's not necessarily true about the ratio of continuous functions, but if they're both continuous at this point and the denominator is not 0 at that point, then you can say f divided by g is continuous at that point, provided that g evaluated c is not 0. And then what does this notation mean? Put the little bitty circle between two functions. F of g. F of g is continuous at x is c if the individual ones are. For instance, if I look at y is equal to the sine of x to the fifth. I know the sine function is continuous for all x. Y is equal to x to the fifth is continuous for all x. So this is the sine of x to the fifth. Continuous plus continuous, continuous minus continuous, continuous times continuous, those are all continuous. We had left and right-sided limits when we talked about functions, so we can have left and right-sided continuity. For instance, this function's continuous for x to the left of 5, I'm sorry, to the right of 5. F is continuous to the right of 5, but not to the left of 5. Or I could say here, this particular function is continuous for x to the left of 2. It's continuous for x to the right of 2, but it's not continuous at x is equal to 2. So we can talk about continuity from the left and the right. Discuss continuity of say f of x is equal to the square root of 4 minus x. Well, it behaves like a square root function, but I've kind of tipped things around in here, so that's going to adjust where my square root function is in the xy plane. Function is defined for all value of x in its domain if it looks like one of our favorite functions. Can anybody tell me how to find the domain of this function? We can only take the square root of things that are greater than or equal to 0. So we're going to take the stuff under the radical sign and say that it has to be greater than or equal to 0. So this function is continuous for x satisfying 4 minus x is greater than or equal to 0. And so if I move the x to the other side, that says 4 is greater than or equal to x, which is the same thing as saying that all x smaller than or equal to 4. When x is 4, the square root of 4 minus 4 is the square root of 0, which is 0. Here's x is 4, I get 0. When x is 0, I get the square root of 4, which is 2. And then the rest of it's going to look like the square root graph, which I was able to draw without picking up my pencil, because it's continuous for all x less than or equal to 4. All right, how about this function? Same for f of x equal to x squared plus 4x plus 3 over x plus 1 if x is greater than or equal to -1. There we go. X squared plus 4x plus 3 over x plus 1 if x is greater than or equal to -1. 2x minus 5 if x is less than -1. Maybe I should go the other way. Let's go this way. Let's make this a strict inequality here. Because of that, I can't have that. Let's put the or equal to here. Fix that. Take the or equal to and put it on the other piece. Okay, so what I know is that 2x plus 5 is continuous for all values of x. That's just a linear segment, right? I know that x squared plus 4x plus 3 is continuous for all values of x. That describes a parabola, it's polynomial. X plus 1 is continuous for all values of x because that's a linear function. So their ratio should be continuous provided the denominator is not 0. There's our suspicious point. There is a value of x that makes the denominator 0. Where is it? At -1. And that's where it changes shape. So we're going to call x is equal to -1 a suspicious point. And that's the only one. That's the only one at which this function is possibly not continuous. So x is equal to -1 is a suspicious point. It's possibly a point of discontinuity. We need to check those 3 things that I wrote up here. A function is continuous at x is equal to a if f of a exists, if the limit as x goes to a exists, and if they're the same number. Okay, so we need to check if f of -1 exists, if the limit as x goes to -1 of f of x exists, and are they the same? Those are the 3 things we need to check. So here we go. What is f of -1? There's a point on this graph because I moved the or equal to down to the second segment. When x is equal to -1, the y value is 2 times -1 plus 5. Okay, when x is equal to -1, is 2 times -1 plus 5. It's 3. To find if the limit exists, we need to look at the limit from the left and the right of that broken graph to see if they hook up or not. So to check this, I'm going to look at the limit as x goes to 1 from the right, and the limit as x goes to 1 from the left. Coming in from the right, I'm looking at this piece. X is to the right of -1 gives me this piece. And coming in from the left, when x is smaller than 1, I look at the other piece. The second limit is the easiest one to take because I can plug the number in and get a number back out. This one is 3 when I plug -1 in. It's a -1 from the left. The first one, if we put -1 in for x, I get -1 squared is 1. 4 times -1 is -4 plus 3 over -1 plus 1. I get 0 over 0. So help me take that limit. 0 over 0 means do more. No factor, right? Are there factors of 3, both with the same sign, that add to 4? 3 and 1. So my factor that is x plus 3, x plus 1. Right. That's -1. Right. X plus 3, x plus 1. So to take that limit, I can cancel the x plus 1s. And then when I do that, I put -1 in for x, and I get 2. So what is the answer to this question here? Does not exist. So if I'm going to discuss the discontinuity, I'm going to say this function is not continuous at x is equal to -1. But everywhere else, it's okay, right? So this function is continuous for all x other than -1. Yes.
Wait, I missed what you did with number 2 to figure out that that was not continuous. Where did you, like, how did you figure that out from getting 2?
I got 2 different limits,
Oh, very
right? You need the limit to exist, but from the left and the right, they missed. So if you were to graph this thing, there'd be a jump in the graph when x is -1. Okay?
Yes.
Now, some of your problems on web work say, here's a function with a variable in the slot. Can you find a value of this particular letter to make this function continuous? So let me duplicate an example like that. Let's take essentially the same function. Find a value of c so that function here maybe I'll just change the slope. So that that function is continuous for all x. My problem with the previous example was there was a jump in the graph. Is there a way I can doctor the number in front of the x so that my limit from the left is equal to the limit from the right is equal to the value of the function at x is -1? It's not a terrible question to ask. We already know what the limit from the left is. The limit from the left is 2. So I need the limit from the right to be 2 and to be the value of the function when x is equal to -1. So we need c times -1 plus 5 to be that number right there. Agree? So that's what I'm going to write. From our last example, we know we need c times -1 plus 5 to be the limit here. So that the limit from the left is equal to the limit from the right is equal to the value of the function at that particular point. So just solve that equation now for c. Subtract 5. I'll write that it's minus c. Subtract 5 and I get -3. And then multiply both sides by -1. And now there's not a jump there. There's a function value. There's a limit, same as the function value. Okay. And all the other points weren't suspicious points. All the other points are in their domains. So we've got a continuous function for all values of x. Okay. So there are some problems like that on your web work. Make your limit equal to the value of the function. That make you think of anything you want to ask? All right, one of the byproducts of having knowledge about continuity is something called the intermediate value theorem. Intermediate value theorem. Just refer to it by its initials, intermediate value theorem. Where are you? There you are. There you are. Kind of says the obvious thing. Pretend that I have a string in my hand, or maybe a piece of wire that's unbroken, and I can bend it. So it's representing my continuous function. The intermediate value theorem says that if at one end, the y value is here, and at the other end of my wire, the y value is here, then by gosh, that wire passes through every y value between this one and this one. It's every value in between. That's what that says. So if f is continuous on some interval from x is a to x is b, with f of a different from f of b, then f attains every y value between f of a and f of b. So there's the picture. Let's put f of a up here. Let's put f of b down there, where this number is a. So that ordered pair is here, and this number is B, so f of B I'm gonna put here. Then you're guaranteed to hit every y value in here. The only way it can move, it could get more than those, but it's gonna get every one of them. In particular, this theorem is handy when these two y values are opposite in sign, because it tells you that there's a 0 somewhere in the interval. We use this intermediate value theorem in something called the root locator theorem. If f of a and f of b are opposite in sign, then there is a root or a 0 of that function in between the interval a and b. And we can find it. We can work at finding it. For instance, I've got an example up here. Oh, don't have an example, I'll make one up. Third degree polynomial, x cubed minus x plus 3. Do we all agree that this is continuous for all values of x? I want you to find an interval of length 1 that contains a 0 of this function. Find an interval of length 1 that contains 0 of this function. Find consecutive integer values at which f of one side is positive, f of the other side is negative. So I'll help you. What's f of 0? F of 0 is 3. So f of 0 is positive. What about f of 1? It's still positive. So I can't claim that there's an interval between a 0 between 0 and 1. There might be, but I can't make that claim. I'm not guaranteed it. The y value hasn't changed. What about f of -1? Still 3, isn't it? What about f of -2? What's f of -2 in this example? Negative something, right? You get -8 plus 2 is -6 plus 3 is -3. Boom, I found a negative y value. There's a negative y value on the interval from x is -2 to x is -1. Because f of -2 and f of -1 changed sign. So it had to get from y is -3 to y is +3 somehow. And it does that by crossing the x-axis. Can't just jump over it. And if I wanted now to find an interval of length 1/2 that contains 0, -2, there's -1, f of -2 was negative. This was positive. What if I wanted to find an interval of length 1/2? I know it gets from here to here somehow. Maybe it does that. Maybe it does it closer to -1. I don't know. What's a good way to find out? put in negative 1.5. See what the sign of that is. Let's pretend we did that. Well, let me just do it. Negative 1.5 is negative 3/2. So negative 3/2 squared is 9/4. This is plus, well, not squared, I went cubed. Cubed, so cube it, cube it, cube it. And that's going to be negative 27/8. And this is going to be plus 3/2. 3/2 over, make that something over 8 gives me 12/8 plus 3. So I get a negative, negative 15/8, which is not quite 3. So that's a positive number. F of 3/2 is positive. So if that's 3/2, I got it positive here, just like I've drawn it, and there's a 0 in there. That's called the bisection method for finding zeros. If I wanted to get it now in interval of length 1/4, cut it in half again. Use this fact that I know about continuous functions. But nowadays, you don't have to do that, right? You got graphing calculations, you just trace and boom, there it is. But that's how that algorithm was programmed initially for calculators and computers with the intermediate value theorem. Okay. You guys done with me for the day? All right, so I will do the section on exponential and log functions next time, and I gave you kind of some skeleton notes that we'll just kind of fill in next time. I usually am real disorganized when I cover that section, and hopefully those skeleton notes will keep me organized. All right, have a good day. This thing unplugged before anybody trips over it.